Hey everyone. So I had to cut my lecture a little bit short on Thursday, but I realized that I wanted to share this last bit with you guys because I think it'll help on the homework and for clearing up in the class the difference between these similar looking equations that we call various versions of Bellman's equation. So the first Bellman's equation is Bellman's expectation equation. So that is u pi of s equals r of s pi of s plus gamma times the expectation with s prime distributed according to the transition probability at s pi of s. And this is the expectation of u pi of s prime. Like I said, this is called Bellman's expectation equation. And you'll see there's no max in here. There's no optimization operation going on at all. So this is only suitable for use in policy evaluation. So if we're given some policy pi, this equation will allow us to evaluate that policy. And I gave you a matrix form of that, which will speed it up and allow it to be done quickly in a computer. The second equation is called Bellman's optimality equation. This is u star of s equals max over a. So now we're doing a maximization. RSA, notice that there's no prescribed policy here. It's just maxing over that action. Plus gamma times the expectation of with s prime distributed according to the transition probability of u star of s. And so this is called Bellman's optimality equation. And if you hear people talk about just Bellman's equation, this is most likely what they mean. So this u star here is the value for the optimal policy. The value for the policy that maximizes the value function. Now, there's two places we use this. We've used it so far in the by hand Bellman backup algorithm. So this is what I did in class, where we start off with some states such as terminal states that we know the value of, and then based on that, we can back up as long as we know u star of s prime for all the successor states, we can back up and find u star of s. Now, the second way that we use this equation is as a certificate of optimality. Certificate of optimality. So if you can prove that a value function satisfies this equation at all states, then that means it is the optimal value function. And we'll talk about why that is in a few lectures. So if you have some value function, if somebody comes to you with a value function and asks you, is this optimal? Then you can evaluate this equation for all states S here. And if it's satisfied, then that is the optimal value function. Okay, so the final version of Bellman's equation is u prime, of S equals max over a RSA plus gamma times the expectation again of S prime and TSA of U of S prime. And this is sometimes called, well, this is usually called the Bellman operator. So, and this is sometimes written as U prime S equals B for the Bellman operator of U S, and then the rest of this equation, the whole thing with the max there. And so basically the difference between the Bellman operator and Bellman's optimality equation is that we're in Bellman's operator, we're dealing with any value function u. So this does not have to be an optimal value function. It doesn't have to be a value function of a particular policy. It's just some function of all the states, or a vector with an entry for each state. And then if you apply this Bellman operator, you get u prime. So if you remember back on this value iteration, the Bellman operator is this equation right here. So it is taking some estimate of the value function that may or may not be correct and applying this operator to it, and that's giving you u prime for that s, and then you repeat it for everything. So this allows us to write the value iteration algorithm in a very simple way. So an even simpler way than the page before. You can say initialize u and u prime, and then just repeat while the norm of u minus u prime, usually the infinity norm, is greater than some epsilon. Then we just reset u to be u prime, and then set u prime to be the Bellman operator applied to u. So this equation is just for one particular state, but this Bellman operator can be applied to the whole value function or value vector. And this is the value iteration algorithm written with that Bellman operator. And so we'll prove next week that this value iteration algorithm always converges, but at any time before it converges, this value function u or u prime is not really meaningful as a value function for a particular policy. We're just updating it to u prime in this way that will cause it to converge. And we'll talk about next week why it does that. So one more thing for your homework, I suggested that you just guess a policy for the MDP that I gave, and then verify that the value for that policy satisfies Bellman's optimality equation. So here, just to complete this, we use Bellman's operator for value iteration. Okay, but in the homework, I'm suggesting for you to guess, just based on your intuition, what a good policy is. And then step one on the homework will be to calculate the value for that. So you'll use the matrix form of this policy, Bellman's expectation equation. And then two, check for all states whether that satisfies Bellman's optimality equation. And then you've proven that you found the optimal value, optimal utility, and therefore you have an optimal policy. All right, hope that's helpful.